Welcome! In this session, we'll be solving problem number 969, pancake sorting. This is an exciting problem that involves sorting an array using a unique operation called pancake flipping. We'll explore different approaches, analyze their complexities, and break the problem down step by step. Let's dive in. In the pancake sorting problem, you are given an array of integers called ARR, which represents a permutation of numbers from 1 to n. The goal is to sort this array in ascending order, but instead of using traditional sorting techniques, you are limited to using a special operation called a pancake flip. A pancake flip involves selecting the first k elements of the array, where k is any value between 1 and n, and reversing their order. Your task is to determine a sequence of k values corresponding to the flips that will sort the array. The solution must sort the array using at most O, n squared, flips, and any valid sequence of flips that achieves this will be accepted. The input is an array ARR, and the output is a list of integers representing the sequence of flips performed to sort it. To better understand how this works, let's look at an example. Suppose the input array is ARR equals 3, 2, 4, 1. To sort this array, we can perform the following pancake flips. First, we flip the first 4 elements, which transforms the array from 3, 2, 4, 1 to 1, 4, 2, 3. Then, we flip the first 2 elements, changing it to 4, 1, 2, 3. Next, we flip the first 4 elements again, resulting in 3, 2, 1, 4. Finally, we flip the first 3 elements, producing the sorted array 1, 2, 3, 4. The sequence of flips performed is 4, 2, 4, 3. This sequence is a valid solution because it successfully sorts the array within the allowed number of operations. Now let's consider another example. If the input array is ARR equals 1, 2, 3, the array is already sorted in ascending order. Since no flips are needed, the output is simply an empty list. In this case, the solution reflects the fact that no operations are necessary to achieve the desired result. This illustrates how the problem can handle cases where the input is already sorted. Let's explore one more example. If the input array is ARR equals 4, 3, 2, 1, we can sort it with the following sequence of pancake flips. First, we flip the first 4 elements, transforming the array from 4, 3, 2, 1 to 1, 2, 3, 4. Since the array is now fully sorted, no additional flips are required. The output in this case could be 4, or depending on implementation, it might include some redundant flips, such as 4, 3, 4, 2. The key is that the final result must be sorted, and the solution must stay within the required time complexity. The constraints ensure that the problem is well defined, the length of the array ranges from 1 to 100, and the array is always a valid permutation of numbers from 1 to its length. Finally, this problem also covers a variety of edge cases. For example, arrays that are already sorted should return an empty list of flips, as no operations are needed. In cases where the largest element is already in place but other elements are out of order, the solution must focus on sorting the remaining portion of the array. Additionally, for arrays of maximum length, such as 100, the solution must still operate efficiently within the O, n squared, time complexity. By handling these scenarios, the problem ensures a comprehensive test of your approach to sorting permutations using pancake flips. To tackle the pancake sorting problem, let's first discuss some approaches we considered. One option is the brute force approach. The intuition here is that since pancake flips allow us to reverse a subarray, we could try to sort the array by exploring all possible sequences of flips. However, this involves generating a vast number of permutations of flips, which leads to an exponential time complexity of O, n. This makes the brute force method computationally expensive and impractical for larger arrays. Given the problem constraints, this approach is simply not feasible. Instead, we can simulate sorting using a greedy approach. Here, the idea is to repeatedly place the largest unsorted element in its correct position. First, we find the index of the largest unsorted element, then flip the array to bring this element to the front. Next, we flip again to move it to its correct position in the array. By repeating this process for the next largest unsorted element, we progressively sort the array. The key observation is that each iteration fixes one element in its final sorted position, and since each flip operation takes O(n), the total time complexity is O(n squared). This greedy approach is efficient, directly uses pancake flips, and aligns well with the problem requirements, making it a strong candidate for our solution. An alternative approach we considered is the divide and conquer method. Instead of sorting the array iteratively, this method involves dividing the array into smaller segments, sorting each segment recursively, and then merging the results. While this could potentially reduce the number of redundant flips, it introduces additional complexity in managing the recursive calls. Moreover, the time complexity remains O(n squared), and given the manageable constraints of n less than or equal to 100, the greedy approach is simpler and more intuitive, making it the preferred choice. Now, focusing on the chosen strategy, we selected the greedy approach because it aligns perfectly with the problem's requirements. The strategy involves repeatedly finding the maximum element in the unsorted portion of the array, flipping the array to bring this element to the front, and then flipping again to place it in its correct position. By reducing the unsorted portion of the array and repeating these steps, we achieve a sorted array efficiently. Each iteration fixes one element, and the number of flip operations is minimal. Although this approach may not minimize the total number of flips, it guarantees correctness and maintains simplicity. With an acceptable time complexity of O(n squared) for the given constraints, this method strikes the right balance between performance and ease of implementation, making it the optimal solution for pancake sorting. To begin with, the problem asks us to sort an array using a unique operation called a pancake flip. A pancake flip reverses the order of elements in a subarray, starting from the first index. The challenge is to sort the array in ascending order using the minimum number of flips. For example, if we are given the array 3, 2, 4, 1, the sorted order should be 1, 2, 3, 4. A potential sequence of flips could involve flipping the first three elements to bring the largest number, 4, closer to the start, and then flipping the first four elements to position it in the correct place at the end. This process is repeated for the remaining unsorted portion until the array is completely sorted. Now, we adopt an iterative, greedy strategy where we repeatedly identify the largest unsorted element and place it in its correct position. To do this, we start iterating from the end of the array, working back toward the beginning. For each position, the task is to find the maximum element in the unsorted portion and ensure it is placed correctly. This is achieved through a series of targeted flips. Once we identify the largest unsorted element, the next step is to reposition it. First, we perform a flip on the subarray that includes the maximum element, bringing it to the front of the array. Then, we perform a second flip on the subarray up to the current position, moving the maximum element from the front to its correct position. For example, if the largest unsorted element is initially at index 3, the first flip will reverse the subarray up to index 3, and the second flip will place it in its correct position at the end of the unsorted portion. By repeating this process for each unsorted segment, reducing its size by 1 with each iteration, we systematically sort the array. This approach ensures that we only focus on the unsorted portion, and with each step, the size of the problem decreases, bringing us closer to the solution. The efficiency of this algorithm lies in its greedy strategy. By focusing on placing the maximum element in its correct position at each step, we simplify the problem incrementally. At most, 2 flips are required for each unsorted portion, making the process predictable and straightforward. While this method may not guarantee the absolute minimum number of flips, it is efficient and ensures the array is sorted correctly. Additionally, the algorithm is space efficient because it works directly on the input array without requiring extra data structures. The only additional variable used is max_IDX, which tracks the position of the maximum element in the unsorted portion. This minimal use of resources makes the approach both simple and practical for small to moderately sized arrays. Analyzing the complexity of this algorithm, we see that the time complexity is dominated by the linear scans to find the maximum element and the subsequent flips. For the first element, we perform one linear scan, which takes O(n) time, and for the second, O(n1), and so on. Summing these together gives us a total time complexity of O(n squared). On the other hand, the space complexity is O(1), because the algorithm modifies the input array in place and uses only a few additional variables. To illustrate, consider the array 3, 2, 4, 1. In the first step, we find the maximum element, 4, at index 2. We flip the first 3 elements to bring 4 to the front, resulting in 4, 2, 3, 1. Then, we flip the entire array to position 4 at the end, yielding 1, 3, 2, 4. This demonstrates the core operations of the algorithm. Continuing with the example, we now focus on the remaining unsorted portion, 1, 3, 2. The maximum element here is 3, located at index 1. First, we flip the subarray up to index 1, giving 3, 1, 2, 4. Next, we flip the subarray up to index 2, positioning 3 correctly, which results in 2, 1, 3, 4. Finally, for the last unsorted portion, 2, 1, the maximum element is 2 at index 0. A flip on the subarray up to index 0 has no effect, and the final flip on the subarray up to index 1 produces 1, 2, 3, 4. The array is now sorted in ascending order. This example highlights how the algorithm incrementally reduces the problem size and ultimately achieves the desired result through a series of targeted flips. This solution implements the Pancake sorting algorithm in Python. The goal is to sort the array by repeatedly reversing subarrays. The Pancake sort function generates the sequence of flips needed to sort the input array. The algorithm works by iterating over the array from the largest number down to the smallest. For each number, it determines the current index of that number in the array. If the number is not already in its correct position, 2 flips are performed. 1. The first flip brings the number to the front of the array. This is done if the number is not already at the start. The length of this flip is index plus 1, where index is the current position of the number. 2. The second flip moves the number from the front to its correct position in the array. The length of this flip is equal to the target value. The function appends the lengths of these flips to the result list, which is returned as the final output. The array is progressively sorted in place by these operations. The algorithm ensures that every number is moved to its correct position in decreasing order, reducing the problem size with each iteration. The time complexity is approximately n squared, due to the nested use of index search and slicing, but it is efficient enough for the constraints typically seen in competitive programming problems like this. Here, we start by defining the Pancake sort method, which takes an integer array as input and returns a list of integers representing the sequence of flips required to sort the array. We use an array list to store the result. The main logic involves iterating from the largest value in the array down to 1, aiming to place each value in its correct position. First, we find the index of the target value using the findIndex helper method. If the target value is not already in its correct position, we perform 2 flips. The first flip moves the target value to the front of the array, and the second flip moves it to its correct position. Each flip operation is recorded in the result list. This ensures that we incrementally sort the array in a top-down manner, with each iteration placing the next largest value in its sorted position. The implementation also includes 2 helper methods. The reverse method is used to reverse the elements in the array between 2 specified indices. This is the core of the flipping operation. By swapping elements at the start and end positions and moving inward, the method reverses the specified portion of the array. The findIndex method helps locate the position of a given target value within the array. It iterates through the array until the target value is found and returns its index. If the input is valid, the target value is guaranteed to exist in the array, so the method should never return -1. Together, these helper methods support the main sorting logic, enabling us to simulate the Pancake flipping process efficiently. Here, we start with the input array ARR equals 3, 2, 4, 1. The goal is to sort the array using a series of Pancake flips, and will record the flip indices in the result array. Initially, the largest number is 4, found at index 2. To bring 4 to the front, we flip the first 3 elements, which appends 3 to result and updates ARR to 4, 2, 3, 1. Next, we flip the first 4 elements to move 4 to its correct position at the end of the array. This appends 4 to result, resulting in ARR equals 1, 3, 2, 4. Now, we move on to the second largest number, 3, found at index 1. First, we flip the first 2 elements to bring 3 to the front. This appends 2 to result, giving us ARR equals 3, 1, 2, 4. Then, we flip the first 3 elements to place 3 in the correct position, appending 3 to result in updating ARR to 2, 1, 3, 4. At this stage, the next target is the third largest number, 2, which is found at index 0. Because 2 is already at the front, we can flip the first 2 elements to move it to its correct position. This appends 2 to result, resulting in ARR equals 1, 2, 3, 4. Finally, the last target is the smallest number, 1, which is already in its correct position at the front. No flips are needed for this step. With the array now sorted, the final output of the result array is 3, 4, 2, 3, 2. This sequence of flips successfully sorts the input array. Now, let's look at a simpler example with ARR equals 1, 2, 3. Here, the array is already sorted. We start by identifying the largest number, 3, which is at index 2. Since it's already in the correct position, no flips are needed. Moving to the second largest number, 2, it's also already in the correct position at index 1, so no flips are required. Finally, the smallest number, 1, is in its correct position at the front, so no flips are needed here either. As a result, the result array remains empty, and the sorted array is the same as the input. In this example, we have the input ARR equals 4, 3, 2, 1. The largest number, 4, is already at the front of the array, so we can directly flip the first 4 elements to place 4 in its correct position at the end. This appends 4 to result and updates ARR to 1, 2, 3, 4. Next, we move to the second largest number, 3, which is already in its correct position at index 2. No flips are needed. Similarly, the third largest number, 2, is already in the correct position at index 1, so no flips are necessary. Finally, the smallest number, 1, is already in its correct position at the front. With no further flips required, the array is now fully sorted. The final output for this example is result equals 4. This single flip was sufficient to sort the array, as the input was already in reverse order and required just one operation to place the largest number in its correct position at the end. To analyze the time complexity of the Pancake sort function, we begin by looking at its key operations. First, the outer loop runs from n down to 1, meaning it iterates n times, where n is the length of the input array. Within this loop, we use the index function to locate the position of the target number in the array. The index function performs a linear scan, making its worst-case time complexity O, n. Since this operation is repeated for each iteration of the loop, its total contribution is O, n squared. Next, we consider the array reversals. In each iteration, we might reverse the subarray up to the target element and then reverse the subarray up to its final position. Both reversals have a time complexity proportional to the size of the subarray, which can be at most n. Summing up the cost of these reversals over n iterations also results in O, n squared. Thus, both finding the indices and performing the reversals contribute significantly to the time complexity of the algorithm. When combining the costs of the index lookups and the reversals, the overall time complexity of the Pancake sort function is determined to be O, n squared. Now, shifting to space complexity, the function operates directly on the input array, modifying it in place. This means no additional memory is allocated for processing the array itself. The algorithm does use a result list to store the sequence of flips, and in the worst case, each element in the array might require 2 flips, one to bring it to the front and another to move it to its final position. As a result, the size of the result list is at most 2n. This bounded memory usage ensures that the space complexity remains efficient. Additionally, the reversed function, which is used for in-place subarray reversal, does not allocate extra memory as it directly modifies the input array. Therefore, the only auxiliary space required by the algorithm is for the result list, making the overall space complexity O, n. Now, considering different scenarios, in the best case, the array is already sorted. Here, no flips are needed, and the index function consistently finds the target in constant time, reducing the time complexity to O, n. However, in the average and worst cases, the algorithm must execute the full set of operations, including index lookups and up to 2 reversals per iteration, resulting in the overall time complexity of O, n squared. Comparing this optimized approach to a naive brute force method highlights its efficiency. A naive method would involve generating all possible permutations of flips and checking which results in a sorted array. This strategy has a factorial time complexity of O(n), which becomes computationally infeasible as n grows. In contrast, the optimized solution applies a greedy strategy, iteratively placing the largest remaining elements in their correct positions through a sequence of flips. By reducing the problem size step by step, the time complexity is significantly improved to O(n squared). Mathematically, this is justified by noting that the algorithm performs n iterations, with each iteration involving an O(n) search and up to 2 O(n) reversals. Summing these costs gives O(n) plus O(n1) plus O(n2) plus O(1), which simplifies to O(n squared). This analysis confirms the efficiency of the greedy approach over the naive alternative. When solving the pancake sorting problem, there are several common mistakes to watch out for. First, not understanding the problem statement clearly can cause confusion. Remember, pancake flipping reverses the order of all elements in the subarray up to the chosen index. Misunderstanding this rule can lead to incorrect assumptions about how to manipulate the array. To avoid this, carefully read the problem statement and confirm your understanding with examples before diving into the implementation. Another mistake is relying on inefficient sorting algorithms. A brute force approach that tries all possible flips can result in exponential time complexity, which is impractical for larger arrays. Instead, focus on finding the largest unsorted element and flipping it to its correct position iteratively. Finally, watch out for off-by-one errors in flip indexing. Pancake flipping may use 1-based indices in some explanations, but your code likely uses 0-based indices. Ensure that you map the problem constraints clearly to your implementation logic and test boundary cases to avoid these errors. Another common pitfall in pancake sorting is failing to account for already sorted sections of the array. Repeatedly flipping parts of the array that are already sorted wastes computational resources and slows down your solution. To address this, keep track of the sorted portion of the array and skip unnecessary flips. Additionally, overlooking edge cases can lead to runtime errors or incorrect results. For example, an empty array, a single element array, or an array that is already sorted are all scenarios that need explicit handling. Testing your code with these edge cases ensures it performs reliably under all conditions. To excel in interviews involving pancake sorting, it's helpful to break the problem into clear steps. Focus on the iterative approach, identify the largest unsorted element, flip it to the front, and then flip it to its correct position. This process minimizes the number of flips needed. It's also important to optimize early. Sorting the array iteratively from the back reduces redundancy and improves efficiency. During discussions, compare the brute force approach with more efficient strategies to demonstrate your understanding of trade-offs. Effective communication is key. Explain alternative approaches, their time and space complexities, and the reasoning behind your choices. This shows depth in your problem-solving skills. Recognizing patterns can also be useful. For example, relate this problem to sorting algorithms like selection sort, where you iteratively find and place the largest element. Lastly, be prepared to analyze the complexities of your solution. The optimal approach for pancake sorting has a time complexity of O(n squared, so understanding why that is the case will strengthen your explanation. Pancake sorting shares themes with several related problems. For instance, LeetCode 969 is the classic pancake flip problem, while LeetCode 912 involves general sorting where alternative methods can be explored. Problems like LeetCode 11, which focuses on finding the container with the most water, and LeetCode 376, which emphasizes subarray manipulation in the context of wiggle subsequences, also require strategic approaches to array manipulation. When considering alternative approaches, the brute force method is a natural starting point. This involves trying all possible flips until the array is sorted. While it's easy to implement, it's computationally expensive due to its exponential complexity. On the other hand, the greedy approach is much more efficient. By iteratively finding the largest unsorted element, flipping it to the front, and then moving it to its correct position at the back, you can achieve a time complexity of O(n squared). However, the greedy method requires careful implementation to avoid redundant flips. Another approach to consider is the simulation-based method. This involves simulating each flipping operation step by step while tracking the state of the array. This approach is particularly useful for debugging and visualizing how the algorithm works. For instance, it allows you to see how the array evolves with each flip. However, it is less efficient overall and is not typically the best choice for solving the problem in an interview or competitive coding scenario. Nonetheless, it can be a helpful tool for gaining insights into the problem or explaining your solution to others. Great job! We've now solved pancake sorting using an efficient and iterative approach. Remember, this problem highlights how creativity and constraints come together in algorithm design. Keep practicing similar problems to sharpen your skills. Don't forget to like, subscribe, and share for more content. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!